Hi everyone, in this video I'm going to solve an exercise of spaceflight dynamics. Let's start reading the text of the exercise. Consider a two-dimensional situation where the Sun is located in the orbital plane of the satellite. What is the length of the eclipse period for a satellite in a circular orbit at 800 km altitude? Expressed as percentage of the orbital period, what is the absolute value of the eclipse period? Data of the problem are the radius of the Earth and the gravitational parameter of the Earth. Now, the important assumption stated by the exercise is that we are in a two-dimensional situation. The Sun is located in the orbital plane of the satellite, and this is well represented by the picture reported here below. The Sun is located at the left of the picture. The Earth generates a shadow region indicated by the black spot on the right. The satellite describes a circular orbit around the Earth. Therefore, the satellite at a certain point will cross this eclipse region. If you assume that the satellite is moving counterclockwise along its orbit, it will start the eclipse in B and it will finish the eclipse in A. Now, let us indicate with delta TE the time that the satellite spends in the eclipse. This is what we are asked to compute. And let us indicate with delta theta E the angle subtended by the arc AB at the center of the orbit. In the figure, this is represented by this purple angle here. Now, let us recall that for circular orbits, there is a simple equation that links the angle subtended by an arc at the center of the orbit with the time needed by the satellite to travel along this arc. So basically, there is a link between delta TE and delta theta E. And this link is expressed by the following equation. Delta TE is equal to delta theta E multiplied by delta capital T divided by delta omega. Now, delta T and delta theta E we have already defined before. Delta capital T is the orbital period, the time needed to complete one orbit. Delta omega is the angular displacement after one orbit. That means that we know that delta omega is equal to, if we express all the angle in degree, delta omega is equal to 360 degree. Now, this equation here can be easily explained considering the fact that the angular velocity of a satellite following a circular orbit is constant. The angular velocity, remember, that is the rate of change of the angular position with respect to the time. Therefore, if we indicate the angular velocity with omega, this is equal to delta theta E divided by delta TE, but is also equal to 360 degree divided by the orbital period, delta capital T. Now, from this equality, we got the highlighted equation here. This equation is not valid for elliptical orbits or parabolic and hyperbolic trajectory. For those, the angular velocity is not constant along the orbit, and the link between time and angular displacement is a bit more complicated to compute. So, move on, and let us indicate delta with delta theta E, let's put it equal to 2 lambda. The reason why will be clear later. Now, to answer the first question of the problem, we need to find the length of the eclipse period expressed as percentage of the orbital period. That is, we need to find delta TE divided by the orbital period delta capital T multiplied by 100. And from this equation that we have highlighted in yellow here, we know that this is equal to delta theta e, that we can write like 2 lambda divided by 360 degree multiplied by 100. So basically, to find the length of the eclipse period expressed as percentage of the orbital period, what we need is just to find lambda, this angle. This can be done easily. Just let us consider from the drawing this triangle CAB that I will report here. CA, and here we have B. Okay. Now, if we call with RO the radius of the orbit, we know that CA is equal RO but also CB is equal RO. So basically CA is equal to CB. That means that this triangle CAB is an isosceles triangle. Now, let us consider the base of the triangle AB, the line AB. And let us identify the midpoint of this line that we call O. This is the midpoint. So that AO is equal to BO. So since O is the midpoint of the base of the triangle CAB, then the line CO is the median of this isosceles triangle. And for an isosceles triangle, the median is also the height of the triangle. So this is the median, but this is also the height, so that this angle here is equal to 90 degrees. Moreover, the median is also the bisector, so that this angle that we call 2 lambda is split in 2 halves by the line CO, so that we have here lambda, this angle is lambda, and also this angle here is lambda. Now, to find lambda, we can just consider the triangle CAO and apply a simple trigonometry. So we have this triangle here, CAO. This is 90 degrees. This is equal to lambda. We can write that CA multiplied by the sine of lambda is equal to AO. CA, we already said that is equal to the radius of the orbit. AO, just looking at the figure here, is clear that it is equal to the radius of the Earth. And now we can find sine lambda equal to the ratio radius of the Earth divided by the radius of the orbit. Let us apply the inverse function of the sine, so lambda is equal to the arc sine, the radius of the Earth, divided by the radius of the orbit. Okay, now the radius of the Earth is a data of the problem. The radius of the orbit is, I will write here, radius of the orbit is equal to the radius of the Earth plus 800 kilometers, the altitude of the orbit. If you're going to replace these numerical values, in this expression for lambda, we find that lambda is equal to 62.69 degree. Now we know what is lambda. We can just replace this value of lambda here, and we find that delta TE divided by the orbital period multiplied by 100, so the length of the eclipse period expressed as percentage of the orbital period, this is equal to 34.82%. And this is the answer to the first question. To answer the second question, we need to explicitly find what is the value of the orbital period. This can be easily done by using the third law by Kepler that says that the orbital period is equal to 2 pi divided by the square root of the gravitational parameter of the Earth, mu e, multiplied by the radius of the orbit that we have indicated with rho, power 3.5. If you're going to replace all the numerical values, we have that the orbital period expressed in minutes is equal to 100.87 minutes. Now we can just say that the eclipse period, the absolute value of the eclipse period is equal to this 34.82% divided by 100 multiplied by the orbital period that now we know, so that the eclipse period is equal to 35.13 minutes. And this is the answer to the second question. So the exercise is finished. If you have questions, doubt, please write me in the comment. See you next with another video. Thank you for watching. Bye.